Hello everyone and welcome to another Würth Elektronik ISOS webinar. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is UV LEDs for disinfection. Our speaker today is Dominik Köck, who is working as product manager in the field of optoelectronics at Würth Elektronik ISOS. He will hold today's webinar and also answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You will find the chat function in the webinar control panel. Today's webinar will be about 30 minutes long. The question and answer session afterwards will be about 10 to 15 minutes. And if you have any questions left after the webinar, just email us at isis-webinar@we-online.com. You will also receive the link to the presentation as well as to the recording of today's webinar only in the next few days. And now I will hand over to our speaker, Dominik, and I wish you an exciting webinar.
Well, thank you, Markus, for the kind introduction. So I'm going to give this webinar today about disinfection with UV LEDs. So you all know that since the start of the corona pandemic, the requirements or the interest for disinfection technologies have skyrocketed. So basically, the UVC LEDs or UV LEDs are a new exciting technology that can be used for disinfection purposes. But when someone tries to design a system for disinfection, they're usually faced with a series of problems. So they don't know exactly how to do this disinfection. So how many LEDs are needed, how much light is needed, how long do I have to disinfect a surface, for example, and also what are the safety requirements. And in this webinar, I'm trying to answer those questions and give you a better feeling and understanding on how UV disinfection works. So first I will start the presentation by explaining what UV light actually is, the difference between UVA, B, and C. Then how you can disinfect using UV light, the biological backgrounds of this. Then which wavelength is the best for disinfection. Then afterwards, I will talk a little bit about the doses for disinfection. The dose is basically the amount of light you need for killing a certain amount of bacteria or viruses. And then I will give you a few applications examples and also simulations to get a better understanding how this disinfection could work like and how long it does take. So in the end, I will also talk a little bit about safety requirements because UV light and especially UVC is quite dangerous. And when designing UVC LEDs in applications, you need to be quite careful. So first, let me explain to you a little bit more on UV light. Here you see the electromagnetic spectrum, where you have on the right-hand side the visible spectrum, and on the left-hand side at lower wavelengths we have the UV light or UV radiation. So the UV light is actually composed, or it's separated into different areas depending on the wavelength, in UVA, UVB, and UVC. So UVC is the one with the lowest wavelength but also with the highest energy. So this UVC is the wavelength that is typically used for disinfection. The UVB is used for horticulture and also some phototherapy applications, but I will show you later a little bit more on this. And UVA is mostly used for horticulture and curing. So currently in our portfolio, we do have UVA and UVC LEDs. You can find them on our website under the match code WLSUMW. And there we have UVA LEDs with different wavelengths from 365 nanometers to 405 nanometers. And now also new, we have UVC LEDs with a peak wavelength of 275 nanometers. So those new UVC LEDs come in two different power groups. So one of the product has 3 milliwatts of radiant flux and the other one 15 milliwatts. So this radiant flux is basically the optical power that is emitted by the LED. So the UVA LEDs that we have that are typically used for horticulture, but also for security and counterfeit detection. And but actually the most applications is in the curing business. So you can cure some glues or adhesives with this UVA LEDs. On the other hand, the UVB LEDs, or okay, we don't yet have UVB LEDs in our portfolio, but for completeness, I will also talk about the UVB light. So this is also used for horticulture, but also for treating vitamin D deficiency. This is actually the part of the UV light that you need for creating vitamin D in your body. So there's also a nice idea about irradiating mushrooms with vitamin B, and then they produce more. Vitamin D, and then you have vitamin D loaded mushrooms, which you can then eat. And another application of this UVB is the phototherapy and medicine, where you can treat various amount of skin diseases. So, but here I want to focus on UVC LEDs, UVC radiation. So this is mostly used for disinfection. You can disinfect, for example, surfaces such as your phone or masks. But it can also be used in food industry. For example, imagine you want to disinfect the shell of the eggs. So if you want to kill off all the salmonella on the egg shells, this could be done with the UVC light as well. There are also quite a few interesting studies that show that actually you can increase the time of storage for fruits and vegetables if you irradiate them with a little bit of UVC light, because then you're reducing the growth of mold. And of course, currently during the corona pandemic, air purification is a really hot topic. So with UVC, you can actually kill off coronaviruses that are in the air. But you can not only disinfect air, but also water. This is interesting for drinking water supplies. So if you have, for example, problems with bacteria building up in your water supplies, such as Legionella, they could be killed off with using UVC light. So let's dive into the working mechanism, how this UV disinfection actually works. So here I have a sketch of DNA. And what happens when the UV photon hits the DNA? It actually splits some nucleic acids of the DNA, and then you have some formation of thymine dimers. So this damage, where we have now those dimers, it stays in the DNA, and if the cell wants to replicate itself, this damage hinders the replication. So basically this DNA cannot be duplicated again anymore if this damage is too much. So basically this cell then is inactive, right? Can't live on anymore. And a similar mechanism happens for the RNA of viruses. For the RNA in viruses, they don't have this thymine, but they have uracil. And this is, but the mechanism is similar to this thymine dimers. So basically what you can do, you can damage the DNA, but also the RNA of viruses. So the question is now, which is the best wavelength for disinfection? There are a lot of studies that show or study the wavelength dependence of RNA damage and also DNA damage for example, bacteria. And they all looked a little bit similar, like the black line I show here. So this is specifically for a certain type of virus. And what you see is actually the most damage can be done to the RNA of this virus by using 260 nanometer light. But some other publications suggest that the optimum wavelength could be around 265 nanometers. So it all depends also on the publication and on the germ. I don't know if it's a virus or bacteria that is investigated there. So for your reference, I also put in the spectrum of our 275 nanometer UVC LED. And what you can see is that there is some overlap between the RNA damage curve and the spectrum. But the wavelength of our LED is not ideal. So of course it would be better if we have 260 nanometers as a peak wavelength. Well, but it's not as simple as this. When you're disinfecting something, you need to take into account not only the correct wavelength, but your LED also has to be able to actually supply enough amount of optical radiation. So basically, it doesn't help you if you have a 260 nanometer LED, which just gives not enough optical power, optical radiation. So then it doesn't help you that you have the correct wavelength. So basically, you need to consider those two things, the optical power output and as well as the correct wavelength. And this is what I show you here in this graph, where I inserted the crosses, which are the wall plug efficiency for a few available LEDs on the market with different wavelengths. And what you can see there is that for 265 nanometers, for example, or lower wavelengths, the wall plug efficiency, so basically also the amount of power, of optical power that is emitted by this LED, is much lower than for our 275 nanometer LED. So actually, to be able to disinfect something, we need to consider now both the RNA damage and this wall plug efficiency. And this is how we get to this combined sterilization efficiency, which is the dashed line in gray. So there, this is basically just the product of the RNA damage and the wall plug efficiency for different LEDs. And what you can see there, that this combined sterilization efficiency is actually maximum around 275 nanometers. So actually the 275 nanometer LED is currently the best technology for disinfection. And this is because the 275 nanometer LEDs, it combines the ability to damage the RNA, but it also has a high output power and wall plug efficiency. And this is because the technology of this wavelength is more mature than other wavelengths. So let's now move on for some technicalities. So when someone tries to design a system for disinfecting something, you can usually break down the question how to disinfect something to the question, okay, I have an LED here. and I have a surface here. How can I disinfect this surface? And the question is, how many LEDs do I need? Which electrical current do I need for the LEDs? Which LED do I take? And also then, how long does it take for disinfection? And all of those answers can be modeled or simulated in the end. And for this, we have, for our UVC LEDs, we have WAV files. So WAV files are three-dimensional files which give you how much light is getting into each direction, or is emitted in each direction from the LED. So basically, you see this in the middle picture. So some of those rays are hitting the surface. And when you put in those WAV files into optical simulation software, what you can simulate is, for example, as shown here, how much light is getting on this surface. So in this case, how much light is getting on it, it's called the irradiance. And the irradiance is given as watts per square meter. So it's actually the power per area that's hitting on the surface. Now for disinfection, not only this irradiance is important, but also the time you apply this irradiance on your surface. So what's really important for disinfection is the radiant exposure or dose in the end. And you can get this if you have a certain irradiance in your system, and then you apply this irradiance for a certain time, a certain exposure time. So you leave your LEDs on for a certain time, and you multiply those two values. Then what you get is the radiant exposure or dose. So it's actually the amount of energy per square meter that is coming into the surface. Now, if you want to disinfect a certain germ, bacterium, or virus, the value that can be found in publications is typically the D90 dose. So the D90 dose, it gives you a radiant exposure in joules per square meter that you need to achieve. And after you achieve this amount of radiant exposure, then you get a certain percentage of germ inactivation. So for example, you want 90% of your germs inactivated. Then what you do, you have to apply the D90 dose to your surface. So for example, if you have a model germ, some bacterium, which has a D90 dose of, for example, 18 joules per square meter, then if you have a system where you have this irradiance and 10 seconds of exposure time, then what you get is a radiant exposure of 18 joules per square meter everywhere in this red area. And this means, because the 90 dose for this specific germ, for example, for this specific bacterium, for example, was 18 joules per square meter. That's why everywhere on this red area, you killed off 90% of this specific bacterium. And if you want to have a higher percentage of germs inactivated, what you need is a higher dose. So you can use the 99 dose for 99% inactivation, or this, for example, the 99.99 for 99.99% disinfection. So the correspondence between those different doses is typically when you go from D90 dose to D99, you multiply by the required dose by 2. So basically, D99 is typically D90 times 2, and then you go on. D99.9 is typically 3 times D90, and D99.99 is typically 4 times D90. Okay. So let's have a look at a list of a few D90 doses for some germs, for some viruses and bacteria. So first, currently, most interesting, I guess, is the coronavirus. And we want to know what is the dose to kill, for example, 90% of the coronaviruses. Well, it's not that easy. What you get from different studies, and even within the same study, you will get a lot of different numbers for this D90 dose. So for example, this one study here that is also referenced in the end of the presentation, they found that the D90 dose can actually vary between 6 and more than 100,000. So there's basically a huge difference of the D90 dose found from different research groups. And this is actually due to different experimental settings. So, for example, you can have some absorbance if you're having your viruses in water. Maybe your water is dirty, and everything can influence the value that you actually receive in the end for the D90 dose. So also for application, it is quite important to notice that the D90 dose might not be a fixed value, but depends on your specific application. But nevertheless, this publication also shows a median value of 37 joules per square meter. And in the rest of this presentation, I will continue to work with this 37 joules per square meter. Now, another thing that needs to be considered is on the right-hand side. I show you the lamp type that was used in those studies. So what you see is that most of those studies were performed using low-pressure mercury UVC lamps. So those are those UVC tubes that were already around for a couple of decades now. And those lamps have been used in the past for disinfection. But so this is also why most of those studies were performed using those low pressure lamps. But now we're interested if these values for the D90 doses are actually also applicable to our 275 nanometer LED. So this is why I show you this as example, this E. coli, where we have the D90 dose measured within the same research group for 275 nanometer LEDs and also for low pressure UVC tubes. And those low pressure UVC tubes mainly emit around 254 nanometers. And what you can see is actually that those values are quite similar. So we can approximately assume that the D90 dose for the D90 doses that I've given here for the low pressure lamps are actually also almost applicable to LEDs. So we can take a similar values for the D90 dose for our LEDs. Okay, so the question is now, which is actually the dose that is recommended? Well, it depends on your requirements. How much disinfection do you actually want? Which germs do you want to kill off? So it's not an easy question to answer how much light you actually need to kill off all of the bacteria. But there's this German water disinfection norm that gives you a value of 400 joules per square meter for safe drinking water disinfection. So this could be a value to work with. So in the future, I'm going to work with those 400 joules per square meter and also the 37 joules per square meter for corona inactivation. So now I want you to get a little bit more of a feeling how disinfection could look like. How long does it take? How many LEDs do I need? For this, I have a model UV panel using 9 of our higher power UVC LEDs. And what I simulate is the the irradiance pattern depending on the distance from the UV panel. And what you can see here first is that if you increase the distance, the area that is getting irradiated is increasing. But also what you see is that the irradiance, so how much light gets on it per square meter, is also decreasing. So this means that even though for a larger distance you irradiate a larger area, you need more time to achieve a certain dose for disinfection. For example, I show you here for a dose of 37 joules per square meter. At 4 centimeter distance, I only need 0.1 minutes, but at 20 centimeter distance, I already need about 1 minute. So this is also shown in this little graph here down at the bottom. What you see here is that the time needed to achieve a certain dose is approximately increases approximately with the distance squared. Okay, now I want to switch over to give you a little bit hints on UV safety. This is an important topic because eyes and skin can be damaged with UV radiation, and especially UVC radiation is quite dangerous. So we learned earlier that it can damage DNA. So actually what you can get when having too much of UVC exposure is you might be getting skin cancer from this. So it's really important that if you have an application where there's light coming out, you have to wear protective equipment such as face shields or gloves and protection suits. And if you're designing the UVC LEDs into applications, you also need to attach appropriate warning labels and also include safety measures so the users will not be exposed to UVC radiation. So an example would be, for example, you have a lamp in an open room and you want this lamp to disinfect this room. And then you need to have a safety measure that switches off the UVC light as soon as a human enters the room. So the human does not get any exposure. There's a directive of the European Council here, which gives you a maximum allowed dose per 8-hour workday. And this is for 275 nanometers, 30 joules per square meter. So if you remember earlier, we said the dose to kill a coronavirus, 90% of coronaviruses, was 37 joules per square meter. So actually this maximum allowed dose is even lower than this dose to kill coronaviruses. So even if you are disinfecting a surface, for example, once, you can already exceed this maximum allowed doses per workday. But I also want to note here that I would always recommend to stay way below this maximum allowed dose, because the damages that were done by UVC radiation, they can add up over time. So maybe you have a little bit of exposure one day and then the next day and the next day. And this can actually add up over decades, and you might be able to see the effects only after decades. I want to show you also as example simulation regarding safety with our UV panel that I showed earlier, to see how fast it's actually possible to achieve this maximum doses. So if you're 20 centimeters away, you can achieve the dose of 30 joules per square meter in 50 seconds. While when you're only 4 centimeters away, you only need 6 seconds of exposure to get this maximum dose. But if you get even closer, you might even be able to get it in below a second. So actually, also already short exposure to UVC light is dangerous and can already exceed the daily limit. So you have to be really careful with this. So let's give you a short summary what we learned so far. We have new UVC 275 nanometer UVC LEDs that can be used for disinfection. And we found that this wavelength is actually a good trade-off between the wavelength and the optimal wavelength, and also the ability to, or the wall plug efficiency. So basically, it's one of the best technology currently for disinfection. Then I showed a few D90 doses for some germs. And there it also has to be noted that those doses can vary a lot depending on your specific applications. Then I showed you that we have WAV files available, which can be used in optical simulations for simulating your system, and then also get information on how much LED you need and how to align the LEDs to get the disinfection result that you want. And in the end, I showed you that UV, and especially UVC light, is quite dangerous, and you need to take a lot of care when working with this. So before we come to the questions, let me show you here a screenshot of our website where you have the UVC and UVA LEDs. And so if you go to our website and under the match code WLSUMW, you can find all of those UV LEDs. So those WAV files will also be available under downloads within the next few days. So if you're interested in those, check again in a few days, then they should be online. And there's also now a new application note available. So if you're interested in more details on UVC disinfection, I could refer you to this application note. There you can also read something about material degradation, for example. So thank you for your, oh, sorry, forgot this. Here for your reference is just the literature. If you want to look up a few of the publications that I referenced, you can do it here. And so now I will have to thank you for your attention, and I hope there are a lot of questions.
Yeah, thank you, Dominic, for your interesting presentation. As you've mentioned, now we would like to turn our attention to your questions. I just saw that we get some questions, and yeah, we will have a look at them. Just a hint from my side, you will receive the presentation or the link to the presentation as well as to the recording of this webinar only in the next few days. So then let's start with the first question. Oh, also the hint, if we can't answer your question now in the live webinar, we will answer it afterwards via email. So you will get your answer for your question. Yeah, then Dominic, let's start with the first question. What material should the protective lenses in glasses be made of to protect against UVC?
So what you want to achieve is, it depends on very much what systems you have. So, and also how many LEDs you use and which type of LEDs you use. Depending on this, you have to include different safety measures or shielding materials. So so typically what you have to think of is that you always have to stay below those 30 joules per square meter within a workday. And you would have to think if you have, for example, a lot of UVC LEDs, that you then might need a larger requirements on the shielding for for the shielding material, so a lower transmission. There are some acrylic classes which are added with some UV absorbers, which can actually decrease the transmission for UVC light. And what I would, it's hard for me to recommend a number because, as said, it depends on the specific application. But you try to have the transmission for UVC as low as possible. And values that I typically work with is a transmission of 10 to the power of -6 as transmission. So there are some acrylic classes with UV blockers added that can achieve this amount of transmission. And I would recommend something like this.
Okay, Dominic, thank you very much for your explanation. Then we will have a look at the next questions. Yeah, then let's go on. Dominic, what kind of plastic material are UV stable or most critical for UVC exposure?
So there is a standard which is by which you can test your materials and how UV stable they are. So in the standard, they are testing for a dose which corresponds to something like 700 disinfection cycles. And what you get there is that some materials show degradation and others do not yet. So the question is, which materials are more susceptible to UVC radiation? And so typically, most polymers will have some negative effect from UVC light. For example, if you take normal PE, it will start to get brown under UV radiation, and also a little bit you will have a little bit of cracks. So typically, on the other side, one of the materials that is more resistant against UVC light are all polymers that have a lot of fluor inside. So, for example, Teflon. This is quite stable under UVC radiation. And actually, Teflon is also quite interesting if you want to design a system where you have a chamber, for example, and you want the walls to be reflecting the UVC light to get a higher irradiance in your chamber. And there you can also use Teflon, which has a quite high reflectance for UVC light.
Okay, Dominic, thank you very much. Then I see some other questions here. Dominic, there are studies suggesting 220 nanometer LEDs might be a safer solution for disinfection. Are they better than the 275 nanometer LEDs?
Well, it's true that there are some studies that suggest that 220 nanometer could be more safe than, for example, 275 nanometers. And this is because the UVC light with 220 nanometer doesn't get so deeply into the skin. So basically, it's getting stopped at the top layer of the skin where you only have dead cells. So basically, it does not reach into the living cells. And this is why it's more safe than 275 nanometer LEDs. But there are a few downsides to this. The first is with 220 nanometer, you can already have some ozone being created by this UVC light. So ozone is also dangerous, which needs to be considered in applications when it's being produced. So this is one thing that needs to be considered. And the next thing is that there are actually no LEDs which have high enough power to be suitable for disinfection with 220 nanometers. So basically, the technology is just not quite mature enough for them to be a viable solution.
Okay, so thank you very much, Dominic. And as we see no more further questions for now, I think we are finished with our webinar. If there are any questions left on your side, you can also just email us at isis-webinar@we-online.com. So thank you very much for your attention today, and I hope you enjoyed our webinar. Also, many thanks to you, Dominic, for your time today.
Well, thank you and have a nice day.
Also from my side, have a nice day. Goodbye.